Let's take a look at these ideal gas law questions. The graph below indicates the relationship between the pressure and reciprocal of volume of an enclosed mass of helium gas at 25 degrees Celsius. Assume that helium behaves as an ideal gas. 4.1. Give the name and state in words the law that is illustrated by the graph. So this is going to be Boyle's law. B-O-Y-L-E-S, Boyle's law. Because Boyle's law is the law that investigates the relationship between pressure and volume when temperature and mass is kept constant. Question 4.2. Calculate the volume of the helium gas at a pressure of 450 kilopascals. So they want to know, what is this volume reading right here? Now Boyle's law is given by the formula P1 V1 is equal to P2 V2. We can get P1 and V1 from the graph. P1 will be 105. V1 will be 50. Because remember, on our x-axis, we have the reciprocal of volume. In other words, 1 over the volume. So what we want is the denominator. So we can substitute 105 multiplied by 50 is equal to 450 multiplied by V2. We can then solve for V2, and that's 11,67 dm cubed. Question 4.3. Use the graph to calculate the mass of helium that was used. So we can use the ideal gas equation, which is PV is equal to nRT. And the reason why we are using this equation is because they want the mass of helium. And if we have the number of moles, we can then calculate the mass. Now PV we can get straight from our graph like we've done before. So 105 times 50, though you could use 450 and the value that you solved for in the previous question, so 11.67, you could use that. You could also work at the gradient, so either one would work. And that's equal to N multiplied by R, which is 8.314, and then multiplied by T. Remember that the temperature needs to be in Kelvin. So temperature is going to be 25 plus 273. Now we can solve for N, and N is going to equal 2,12 moles. Now from the number of moles, we can get the mass. Remember that number of moles is equal to mass divided by molar mass. Helium has a molar mass of 4, so M divided by 4. We can then solve for M by multiplying by 4, giving us an answer of 8,48 grams. If you like this video and you want more videos like this, be sure to subscribe, share, and like this video. Okay, let's move on. Question 4.4. Copy the graph in your answer book. Label this graph A. On the same set of axes, draw the graph that will be obtained if the temperature is conducted at 35 degrees Celsius. So they've increased the temperature. So let's sketch this out. 4.4. So here's our original. So this is the pressure. This is the reciprocal of volume. And this is graph A. Okay. What does the temperature do if you increase the temperature? So let's think about gradient first. So if we work at the gradient of this graph, P and 1 over V, remember that gradient is Y divided by X. So on my Y-axis, I have P. On my X-axis, I have 1 over V. P divided by 1 over V is the same as PV. So this, the gradient is PV. And from the equation, PV is equal to nRT. Since we know R is a constant and the mass of the object, or the mass of helium, is not changing, we can say that the gradient is going to be a measure of the temperature. So the higher the temperature, the steeper the gradient should be. So graph B should have a steeper gradient like so, since it is at a higher temperature. Okay, now let's look at 4.4.2. 4.4.2 says a real gas such as ammonia is used. So how will the graph deviate? Now we know that real gases will deviate from ideal gases at low temperatures and at high pressures. So there should be a deviation. Okay, well, let's look at what's going to happen. If we increase the pressure, right, or we decrease the volume, right? Let's go with increasing the pressure, right? So we're increasing the pressure, we are going up this way. Remember that increasing the pressure means that the particles are going to be closer together, right? They're going to collide with each other more because they're going to be closer together. What then happens is that the intermolecular forces, or the force of attraction between the particles, is going to be stronger. So we're going to have a stronger force of attraction, right? And remember, for ideal gases, we ignore the force of attraction, or we ignore the intermolecular forces. So for a real gas, if you increase the pressure, the particles will be closer and the force of attraction is going to increase. Now, if the force of attraction increases, then you're gonna cause the gas to liquefy. So the gas will liquefy. And if it liquefies, then the volume will increase. Now, how will that look on our graph? Remember, on our x-axis, this is the reciprocal of volume. So if we curve the graph this way, it means that the reciprocal of volume is increasing. That means volume is actually decreasing. But if volume increases, what should happen is that this curve, or this graph, should curve upward like this. Thanks for watching, everyone. I hope you found this useful. Be sure to like, share, subscribe, share this with your friends, and I'll see you in the next one. Bye-bye.